Okay, let's talk about molecular formula calculations. So if you're going to calculate a molecular formula, first step, you need to know what it is, especially as opposed to empirical formula. So you can think of it as telling you how many atoms of each element are in a molecule, as opposed to an empirical formula, which would tell you the lowest ratio of atoms in a molecule, or the different types of atoms in a molecule. So these are examples of formulas for compounds where the molecular formula is different from the empirical formula. These are the same compound, it's just that this is what's actually in it and this is the lowest ratio, or this is what's actually in it, C8H18, this is the lowest ratio, C4H9. So this would reduce to CH2O if you reduced it all the way, but we leave it like this sometimes to show it's actually in there, whereas other times it does serve our purposes to reduce to the lowest ratio for certain kinds of chemistry. So neither one's wrong, it's just that they have different uses for different circumstances. And they're not always different. And there are some compounds like water, for example, where the molecular and empirical formula is the same, as in this is the lowest ratio and this is the actual number of each element in the compound. So, having mentioned that, how are you going to do calculations with this? Well, you'll need that information. The molar mass is necessary to successfully calculate what a molecular formula is. Now, why is that? Let's look at that. Here's the question that we're going to look at for the example. Notice, okay, so find the empirical formula, and it gives you the molar mass. This is the information you're going to need to turn that into a molecular formula. So, how are we going to go about doing that? Well, let's start with the fact that this, if you add up 2 phosphoruses and 5 oxygens, this diphosphorus pentoxide is going to have a mass that actually differs from the molar mass. We call this the formula mass. And sometimes they're the same, sometimes they're different. If they're the same, then empirical and molecular formula are the same. And if they are different, then empirical and molecular formula are different. So the way the math is going to look to figure this out is we're going to be like, we notice that the given molar mass, when we compare it to the formula mass, like we divide the bigger one by the smaller one, it's twice as big. It's almost exactly twice as big. So if the molar mass is twice as much as the formula mass, then what we can do is say, well, that must be because the actual formula is twice as much as the empirical formula. So for that reason, we just take the empirical formula and multiply by 2. So 2 phosphoruses become 4, 5 oxygens become 10. And that is what you would box as the correct molecular formula for this. Now, notice how it gives you the empirical formula already done. Isn't that nice? Realistically, on a test, you're calculating your own. So a test question might look a little more like this. Note, no empirical formula given, but they do give you the molar mass. You do need this to find the molecular formula. So, sorry. What you're going to look at here is a situation where you need to find the empirical formula first, then you use this to turn empirical formula to molecular formula. Here's what that looks like. Just as we did in the other example, it looked like this. You start with being like, oh, percent, cool, we'll do a 100 gram sample, just replace percent with grams, because if it's 100 grams, 4.07% is 4.07 grams, cool, okay. So you just say it's grams, and then convert each one to moles, so you grams, do what you gotta do with molar mass to make sure gram cancels gram to give mole in the answer, so you find out how many moles of each of the different elements, and there we've done it that way. And then you take the moles of each of the elements, divide by the smallest number. Oh my God, it's a unitless number, right? It's the one a few times you can use one. And then what you do that, you get this ratio. And this is what you use to come up with your empirical formula. So that's the ratio, a 1 to 2 to 1 ratio for carbon, hydrogen, and chlorine. So that's your empirical formula. And this is the one that you then take and add the molar mass for. So you found this empirical formula. So that's 1, I don't know why they're out of order, 1 carbon, 2 hydrogens, and 1 chlorine. When you add them together, that is the formula mass. And this formula mass is what we compare to the molar mass that was given earlier in the calculations. So, oops, there you go. So the actual molar mass that was given to you as part of the question was 148.44. So we take this divided by the smaller calculated formula mass. We notice it is 3 times as big. So we just take the entire equation, it's not the equation, sorry, the formula, and multiply by 3, which means 1 carbon becomes 3, 2 hydrogens become 6, 1 chlorine becomes 3, and this is what you box as your correct molecular formula, and that's how it's going to go. That's it.